York Festival of Ideas. I'm Josie Rawes, I'm from the University of York, and I'll be chairing the event for you today. And it's my great pleasure to welcome you in person today as well. Today's event is supported by the Institute of Engineering and Technology. The IET is the largest multidisciplinary professional engineering institution in the world, and the North Yorkshire network of the IET is a proud sponsor and collaborator of the York Festival of Ideas. So we're here today for the Back to the Moon talk. Joseph Silk is the Homeward Professor of Physics and Astronomy at Johns Hopkins University. He studied at Cambridge, earned his PhD at Harvard in 1968, and was a postdoctoral fellow at Cambridge and Princeton before teaching at the University of California, Berkeley, and the University of Oxford. He's written or co-authored over 500 publications, and his research has helped to transform cosmology into a high-precision science. He was awarded the 2011 Balzan Prize for his pioneering work on the infant universe, and he spends most of his time at the Institute of Astrophysics at Paris-Sorbonne University. And so, Joe, over to you.
Okay, thank you so much for that introduction. Okay, so it's a pleasure to be here, and my job is going to be to try to inspire you with our current exploration of the moon, which has just grown dramatically in the past couple of years alone, with an amazing future ahead of us. And so in some sense it's going to be maybe, I would say, of order 2 decades before we have mass travel of tourists to the moon. But, you know, look forward to that eventually, because we're going in that direction. There's just no doubt about it. Anyway, I'm going to focus more on the scientific aspects, but tell you a little bit about the political aspects too as we go along. Anyway, so where did all this begin? So let's just try to remember Kennedy, this inspiring ovation, partly out of fear of the Russian impetus, because this was at a time when Sputnik had been launched, and the Russians clearly had the monopoly at that time of launching satellites around the Earth. So Kennedy had the vision, he wanted to overtake the Russians, and he had the vision to see further and said, the moon is my target. We choose to go to the moon in this decade and do the other things, not because they're easy, but because they're hard, because that goal will serve to organize and measure the best of our energies and skills, because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one that we intend to win. And indeed, win they did, as you know, with the Apollo project, which over the next 5 years began from virtually nothing to getting the first men on the moon. And this is one of the iconic images that came out of the Apollo project, Earthrise on the moon. Now, not much else was left behind on the moon apart from an American flag, a few footprints in the lunar regolith, and the various crash sites of 1 or 2 of the landers on the moon. But nevertheless, the wheel is turning, and we're going to do this again, but in a much, much bigger way. And I'll try to explain as we go along why in those early days it was just this dramatic, really politically motivated thrust that got the first humans on the moon. It was a hugely expensive effort. It took a major fraction of the budget of the US to do that. Something like 4% of the gross national product was involved. We will never repeat that again. Now, since then, we're putting money into space at a more modest level, but nevertheless, our aim is again the moon. So why do we want to go there, and what will we do there? Well, I am hoping that one of the things that we'll do is to put telescopes on the moon. I'll try to justify that for you, but you'll see there are many other things you can do on the moon that are very important for humanity, actually. For example, we're running out of certain resources on the Earth. It's dramatic. I mean, your cell phones, etc., your television monitors, all this depend on rare earth elements as minor components, but crucial components, and these are running out on the Earth. If you take the long-term view, in 1,000 years, we really will have a problem. On the moon, there are vastly more resources, because the moon has been bombarded by, rocks over many, many years, and they deliver these things onto the surface of the moon. There are huge supplies there, and I'll explain that to you in a moment too as we go along. And you may wonder about the expense too. Well, I mentioned it was the Apollo program was this dramatic part of the US budget in the first 5 years, but then it faded away. Once we got to the moon, launched by Kennedy's dream, then that was the end, really. There was, after that, what would you do next? There was no real vision of that. Let's just continue. There are other pressing activities needed on the Earth. Ever since then, we've been developing the space program. So have other countries. I'll explain that in a moment too. And going along at this level, it's taken 50 years, but we are now entering what we are calling the Artemis era, post-Apollo, which will take us back to the moon within the next 3 years, actually. And it's quite likely, it's planned that in 3 years' time, we'll have astronauts on the moon. They will include women, that's for sure, and minority people too. That's being planned. And it's not just the US, it's the US and China who are in competition to do this first. So that's the current news. So it's a very exciting time, and we'll be doing more things on the moon as time goes on. Okay, so what I'd like to do is to give you some background as to why I think it's so important to go to the moon as a scientist. And the idea is that there are certain questions that we really want to answer about the universe. Maybe the most important questions humanity's ever posed, I would say. Okay, and what are these questions? Well, one of them is, how did the universe begin? We all know about the Big Bang theory, which is this amazing evidence for the expansion of the universe, inferring that it began as a very, very dense, dramatically dense region a long time ago, 14 billion years ago or so. But, how did this happen? Is our theory of this really true? We have to peer back in time to look at this. And I'll show you that we have to peer back with our big new telescopes way further than we can at the moment. Now we're looking back into the first stars, the first galaxies in the universe with the latest big telescopes in space and even on the ground. But one can go back further. One can go back to before there was any light at all in the universe, what we call the Dark Ages, where there were most likely clouds of gas assembling together to make the first galaxies. And that's where the secrets lie of our beginnings. And so that's one thing we can only do from the moon, as I'll show you in a second. And then there's another amazing question, maybe even more important, which we've been asking for a long time now, thousands of years actually. Are we alone in the universe? Are there other beings out there? So over the past decade especially, we've discovered enormous numbers of planets beyond the solar system. We call them exoplanets, and some of them are very similar to the Earth as far as we can tell. That is to say, they're not too far from the host star, which is like the sun, not too close, so they won't be burnt to a shred, etc. And they have atmospheres, we can tell from our current observations. So they're ideal possibilities for life. But is there life? We have no idea, and we have no idea of predicting this. The only thing we can do is look. Okay, we have to go out there and search for this. And I'll argue that this will need such enormous telescopes that, again, the moon is probably our only bet to do this, okay? Building telescopes on the moon. So that really is what I want to try to justify to you now. Okay. So let's begin with the brief message about the universe. So you can see here that this is a sketch of the Big Bang, okay, beginning from some dramatic explosion some 14 or 15 billion years ago. And as time went on, stuff condensed out of the universe to make clouds and stars and galaxies today. And so this is the story of the universe. And before the galaxies, there was darkness. And then you run into a point where there's a fossil radiation from the Big Bang, which you can see as a weak, very weak glow in the radio region, actually, in the microwave region, just discovered, again in less than 40 years ago or so. And in this region, before then, it's like a fog, but you can't see back any further. But what you can do, we think, with the next generation of discovery, is look into the Dark Ages to tell us how all these structures began. And it's by studying the Dark Ages that we'll even learn more about the beginning and this mysterious theory that we call inflation, which is the best theory we have for explaining how the universe began from such a small and dense region to a very, very huge one, but we have no proof that it really occurred. It's the one theory in cosmology that remains really to be understood better. So that's what our challenge really is. And to put it in a slightly more specific way, structures began. You can see this maybe represents a cartoon of the size of our galaxy today. But as time went on, here we go back in the past, many smaller things merged together. So this is roughly where the first stars were, merging together to make a big galaxy. But before then, what was there? It's what we call the Dark Ages. And then when we look back further, we see the fossil radiation from the Big Bang, which is beautiful. It's got tiny hot spots and cold spots in, which represent the seeds from which all this stuff grew. So we see, if you like, the roots back here. We don't know how they really developed, but then we see the galaxies, and way back is a big question mark because we just do not understand at the moment the details of how things really expanded so enormously. We have a theory, but we need to prove that theory. So that's the big question there that we have. Okay, so that's what I want to tell you about our big question about our beginnings. Now, what about the second question I said, which is, are we alone in the universe? So it's a really profound question because, it seems absurd to think that only humanity should populate this enormous universe with what we know now are billions of planets in our own Milky Way galaxy. Many of them not dissimilar from the Earth. Could there be life on them? Suppose there were life on them, then the chances are, because that life, those stars around which the planets orbit, half of them are much older than our sun. Our sun is, some 4.5 billion years old, but many of these stars around us with planets might be 6 or 7 or 8 billion years old. This means that on those planets, if there were life, it would have much more time to evolve than life on the Earth, billions of years more. Now, all that we know about life on the Earth, we measure in terms of thousands or hundreds of thousands of years, for basically our early origins. But imagine if some life out there on another planet had billions of years. Who knows what it could have achieved or turned into had it not, of course, destroyed itself on the way, which is another option for life, as we only know only too well by what we're doing on the Earth. So that's the question, and this was posed most graphically by a famous physicist, Enrico Fermi, who was basically the pioneer of nuclear energy, radioactive energy, and which even led to atomic bombs and so forth. And so Fermi posed the question, where are they? If there were other aliens in the universe, there are so many possibilities for them. We should be, and they've had so much time to evolve, we should be seeing them. Walk down the streets of New York, where are they, as he said. And there was no evidence at the time, apart from the occasional, news about flying saucers or whatever, which was rapidly shown not to be a real phenomenon. And so that was a question that has to be answered. And the only way to do that is to build telescopes that are large enough to look at these distant planets and see if there are signs of life on them. And I'll explain what those signs might be in a moment, but they might be, for example, oceans or whatever, or atmospheres with certain ingredients in that are evidence of life. For example, suppose you studied the atmosphere of some distant planet with spectroscopy from your super big telescope, you might find evidence of industrial pollution in that atmosphere, right? So that would be an interesting, or you might find radioactive debris from some hot bomb explosion or something. There are various ways of tracing, life far away. You just need enormous light collecting power, really big telescopes to do this, and that we don't have at the moment. So this is perhaps the only way forward. Now, it's not just telescopes, okay? So obviously we want to go to the moon. We're primarily driven by other reasons. What are these other reasons? So one of them is that there's a continuing ambition to explore the solar system. And what we want to do, or what our space agencies want to do, is go to Mars and beyond, okay? Now, Mars is a really, really dangerous journey. It takes you 9 months to get there, but the chances are, in that 9 months, you'll be exposed to so much radiation from space that you will end up on Mars riddled with cancers and be totally useless if there are humans on that voyage. So we have to prepare for that. It's going to take us 100 years probably to get ready for that journey. There are ways of working against this, but it will take a lot of time. In the meantime, the moon is there, and the moon is very useful because not only is it a wonderful place for exploration, it's a way of getting ready for Mars, because the moon has got low gravity. It's a good place to launch your next generation of rockets from. And in particular, it's an ideal site for rocket fuel, because we've discovered in the past few years there's lots of ice on the moon in dark craters. Ice is basically hydrogen and oxygen. You liquefy that, you have no shortage of solar energy on the moon to do this, and you can make rocket fuel, all you need to then help you travel through the solar system. So that's one of the motivations for going to the moon, as a stepping stone eventually to go much further afield. And then another reason is that there's immense pressure now for tourism, amazingly, on the moon. So right now, a ticket to the moon, or so far just to go around the moon, for example, you can buy a ticket already from the companies like StarX or whatever. But this ticket, which will cost you several million, is obviously for the very richest people in our society. But there are a number of those who are desperate to go far into space as far as they can, even for a voyage around the moon. And eventually, one of the things we will do is develop, hotels on the moon, I imagine, in the next 30 or 40 years. And we'll have mass transport also, as I'll show you in a second, also as our rocket get more massive and more reliable, etc., able to do mass transport. So all of that is feasible, and as we know from the history of air transport on the Earth, you may start off as something which is reserved for the rich, but eventually mass transport becomes possible as we learn how to do this much better. And so right now is a bit of a dream for any average person to go around the moon. Right now, that's for the multi-millionaires only, or the billionaires only, who are buying the tickets as we speak. But in the future, that's going to change dramatically as other countries get involved in this too. And I have both China in mind as well as NASA and other countries too. So resorts on the moon, that's going to happen eventually. Imagine playing golf on the moon. You can whack a golf ball for a mile or so. It just so there are many reasons to do this, and go in your loon buggy over lunar terrain, etc. Great things to do. Mining, okay, so we want to mine on the moon. Why do we do this? We're running out of rare elements on the Earth. Semiconductors, rare earth elements, they're crucial for our style of life on the Earth, for the more technological things that we do. We have, europium, one of them, has a 1,000-year lifetime left on the Earth. What is more, it's a highly toxic process to mine these rare elements on the Earth. Not every country is willing to do this. So far, it's really limited in the countries that are willing to do this on the Earth. And China, for example, dominates the world market in rare earths now, and that's unlikely to change very, very dramatically. And besides which, as we run out on the Earth, it'll get rarer and rarer, more expensive to do these things. With the moon, with this huge supply, will be an incredibly important reservoir for mining resources in the future. Now that brings other problems, of course, such as pollution and all this stuff that we'll have to control. I'll come to that later too. And then finally, low gravity on the moon means one can, again, these are the plans of our space authorities, one can do manufacturing of various things that might be much more difficult on the Earth. Even things as, artificial hearts, whatever, and other artificial parts of the body can be done much more easily in a low gravity environment, for example. And there are many, many other examples of why we might do these things on the moon. But my argument today really is that I want you to think about telescopes. Why is the moon so important? That's because there's no atmosphere on the moon. Okay, so the atmosphere is what causes enormous problems on the moon, on the Earth, as you all know too well. In York, lots of rain, etc., etc. You can't see the stars that frequently during the year. If you go to some really dry and arid and high part of the Earth, you have a much better job. But there's nothing like the moon, because there the stars don't twinkle, they're points of light, and you can see in regions of the spectrum that are totally blocked out by the Earth's atmosphere, such as the infrared. You can just have this amazingly clear view of everything in the universe from the moon. And it's not just ordinary telescopes. The other thing the Earth does, which is a problem for radio astronomy, is it's got this ionosphere. It's a plasma blanket, part of the atmosphere, which basically refracts radio waves, especially at the lower frequencies. You can hear this buzz sometimes when you tune into your TV or your radio and you're in between channels. That buzz is from the ionosphere, and it prevents you from observing the universe very clearly. If you go to the moon, you have a much better chance. There's no ionosphere around the moon, so you can see further into the universe. So that's another great reason for going to the moon. And so these are the reasons we want to build telescopes on the moon, really. It's just as such. And that way we can hope to address some of these big questions about the universe that need huge telescope-like collecting power to address. So, let me tell you a little bit about the new discoveries on the moon. First of all, contrary to what you might imagine, the moon is not just an arid desert. There are huge reservoirs of water. And so this is one discovery to show you the international nature of this quest for the moon. This was already a decade ago, but an Indian probe was the first to discover evidence of water on the moon, water ice on the moon. By measuring hydroxyls, and since then other countries have followed this up and confirmed all of this. And these are mostly in deep craters which have rims so high that they're shielded if they're not far from the poles of the moon. The sun is always low in the horizon, so the craters are always in shadow, in dark actually, and at the bottoms there's lots of ice. And so that's a great reservoir, again, eventually for fuel, or for living on the moon. I mean, ice is great if you need water to live, actually, and so that's a crucial component. And so these craters, which have the ice and are not too far from the poles of the moon, and there are many hundreds of these craters, have another intriguing property. And so it turns out that they're here's an example of some of these craters near the South Pole. They all they've been named. You can see there's after various earthly personalities. For example, some of the Russian discoverers who first mapped the moon, Shoemaker, and the Shackleton crater here somewhere, which I'll show you a close-up now. So here's the Shackleton crater. So here's an example of a crater which is 4 kilometers deep, okay, and it's 21 kilometers across, okay, totally dark, okay, in the center. Because it's dark, it's really cold as well, and it's got very high rims, okay. The rims are several kilometers high, and the rims are always in sunlight, so the sun at the poles never gets too high or below the horizon, and the rims always see the sun. So you have a source of solar power which you can pipe down to the crater bottom and do whatever you want to do in the total dark and cold. Maybe it's easier to live in that crater than it would be in some average place. You need some sort of shielding, but it's a great site for building telescopes and for mining water too, for that matter. So you can imagine there might be some competition at some point for resources in these craters too. I'll come back to that too. And finally, these craters are really cold. So here's a thermal image from a NASA probe, and the temperatures in the center of that crater are 30 degrees above absolute zero. That's minus 270 centigrade. Okay, hard to believe that that's the sort of chill that you need, that the astronomers love to get their hands on to build infrared telescopes that need to work at very, very low temperatures, and so on. But so it's an intriguing property of these craters. They're cold and dark, and this is all the time, okay? They're in permanent shadow. So they're a very interesting place where you might want to do science and perhaps mine water as well. But that's another story. Okay, so and then what about mining on the moon? Well, okay, so I mentioned that we're running short of these rare elements on the Earth. You can see the reserves we currently have for rare earths. China has 50 megatons. The US has 14 megatons of known reserves. But these will not, even if we were to mine all of these, they would exhaust them all in tens of thousands of years. If you take the long-term view, we really need to explore resources for these. And the moon has wonderful resources because of this continual bombardment over the eons by asteroids, which deliver many of these and leave them on the surface of the moon. The Earth got reshaped completely over this time by volcanism, etc., etc. So these reserves get weakened and diluted, etc. On the moon, they're all there, and we have of order 1 trillion tons. I mean, that's hundreds of times supply on the Earth. So that would keep us going for a very long time indeed in the future. So that's one reason the mining companies are very excited about going to the moon, as this will be a great thing to do. And then going back to what else we will do on the moon, the plan now is not just to go there and walk around for a bit and come back, but actually to develop habitations on the moon. So here's one European Space Agency concept of these habitations. They're domes with very dense roofs to shield from the micrometeorites, etc., and radiation, etc., and people will be living inside. And Europe has just approved a transport system, and you can think of this as a giant lunar truck, if you will, except this carries a 1.5-ton payload from the Earth, and then will be delivered on the moon. Should be ready by 2030 or thereabouts, and it can carry 1.5 tons, and these will be used to build things on the moon. This is again an artist's concept of that from the European Space Agency. So that's the sort of thing we're looking up to on the moon, and it's going to be a dramatic change for the way we talk about the moon in the future. Okay, so here is another fascinating point about what the science we're going to do on the moon. It turns out that if you want to do radio astronomy, why do you want to do radio astronomy? Because that's the only way to see the dark ages. We have radio signals there's no light there, so you can't look for stars, but you can look for these clouds that are building blocks of galaxies. And those you do with radio signals, so-called 21 centimeter signals, except those signals are highly stretched as the universe expands, and we receive them now not at 21 centimeters, but at meter wavelengths, the same sort of wavelengths that you receive TV on, etc., which means you need antennae that are, typically meters long, that sort of thing. And we do that all the time on the Earth, of course, but if you want to look beyond the Earth, you have a real problem. You've got the ionosphere of the Earth, which blocks you, so you want to go to the moon, but you've also got all the radar and TV stations and radio stations, etc., on the Earth, which give you a terrible background noise, which prevent you from seeing very faint things far away. Now, the one place on the moon that's shielded from all of that is the far side of the moon. So the idea now is to go to the far side where you never see the Earth and you don't have the ionosphere, and that's the ideal place. And people have said it's the best place in the entire inner solar system to do low-frequency radio astronomy, to look at the distant universe, see the dark ages. So that's the rationale for this, and that's why we want to go there and do things. And because radio astronomy is something that to astronomers now it's routine, right? We've been practicing this for many years, and technologically it's very simple to do. We understand these simple antennae, etc. We know how to build them, and we know how to correlate the signals together to make images and things. We do that routinely. We think we can do that very easily on the moon. It's just a short step in our technology. So indeed, why will we do this? Well, this will tell us about where galaxies came from, our beginnings, basically. That's why we want to do this. From these hydrogen clouds that came together to make the first stars, the first galaxies. We're looking before then, as we look far away, we look back in time, and so this will get us much closer to our beginnings, which is one of the big questions that we have. Where do we begin? Okay. So this, again, here you can see the near side and the far side of the moon. These are the Apollo landing sites from 50 years ago, where we went to different parts of the moon, and astronauts got out and walked around a little bit around each of these landing sites, and they did a little bit of science, but not very much, and that, that all stopped after 50 years. This is the far side, totally unexplored, except for one Chinese experiment that did land there in 2019. Nothing has gone there since. And this is where we're planning to go next, to look maybe in craters or maybe anywhere else to put radio telescopes. So let me explain why and how we will do that. Okay, so here's the how, okay? We can do this on the Earth. It's not a problem. So the most ambitious telescope we're building on the Earth right now in the radio is called the Square Kilometre Array. And that simply means it's a telescope that's a kilometre across, but it consists of many small telescopes, dipole antennae basically, like your TV aerials really. And there are up to a few 100,000 of them being planned. And this particular one is a design that's being under construction now in Western Australia. And you have to choose a place on the Earth which is really isolated from radio signals, from humanity, from habitations, whatever. So they found this very remote place in Western Australia to do this. One or two people live within 100 kilometres or something of the site. So it's essentially deserted with little radio interference. And so this is under construction. So we can do this on the Earth. We have no problem with this. But to see the dark ages, we better go to the moon. So it shouldn't be that big a stretch to do the same thing on the moon. Here's a design. And so this is on the lunar regolith, and the idea behind this design was you have a lunar rover lay out strips of mylar, it's a very sophisticated sort of plastic, on which are imprinted by a 3D printer dipoles, okay, just simple wires, which are basically act like antennae. You have to correlate all of them together with either by lasers or with cables, and then send the signal back to Earth, for example, or analyze it on the moon. So it turns out that to get this to work, to do our job on the moon, you want maybe 1 million of these, but that's the same order of magnitude we can do on the Earth, and you need to spread this over about 100 kilometers. Well, this is already over several kilometers. So it's a simple step beyond what we're doing on the Earth. We can do this on the moon. Now, it's not so trivial because you get this stuff to the moon. So that's one of the problems, transport. So there are some ambitious ideas, like maybe you can even do the manufacturing on the moon eventually, or as you'll see in a second, transport is rapidly going through a revolution, so it may become feasible to ship this stuff to the moon with our next generation of supermassive rockets. Okay, here's another example of a vision for the moon. Again, a design only, but you all have probably seen pictures of Arecibo, this giant kilometer-sized radio telescope on the Earth in Puerto Rico, which unfortunately collapsed several years ago. But there's a similar one that's been built since in China, very much like this, but on the Earth. That is to say, it's a natural bowl on the Earth, and you basically fill that bowl with sort of a semi-spherical grid of wires, and you suspend an antenna from the rims. And so the same idea can be done on the moon, where you have this great advantage that there's no ionosphere, and you go to the far side to avoid all the radio noise, etc. And this is what you can do. You basically go to a crater that's 5 kilometers across or something on the far side, and you suspend from the rims the receivers. Okay. And this is what you need to map out the distant universe and look for the very faint things that might be the signals from the beginning. Okay, so this plus this other idea of having a massive array of small telescopes, they both do different things that complement each other. You need them both actually to really bear in on the most distant signals, both types of telescopes. So you have two different types, one of many, many smaller antennas, possibly easy to build, but this also monolithic one, which in principle seems very straightforward. We've done it on the Earth again more than once, and so we should be able to do this on the moon. Okay, so those are the sorts of adventurous things we're thinking of. Now, let me now turn to the origin of life. So we're very hopeful that we'll find indications of life on planets other than the Earth in the solar system. So far, we haven't. So far, there's no evidence on the moon for any origins. We haven't found any bacteria on the moon, whatever. Mars, we've looked at very carefully. So far, nothing directly indicative of life, okay, on Mars. The future, the next decades, we will dig deeper on Mars. We'll look for evidence of fossil bacteria. We know Mars once had an atmosphere, so, long ago it might have had life, but no evidence so far. Another place where we speculate that we might look for life is there are one or two moons, which in this case one around Saturn, which are incredibly icy. And so these are covered by sheets of ice. And we know that below that ice there's water. And we know this because there was a rocket was sent there from a recent probe to Saturn that crashed into the ice, and plumes of water came up. So we know there's under ice water, oceans of it, on Enceladus, and the hope is, could this be a place? It's our best chance of finding life in the solar system, actually, in the water. And there are experiments underway, massive experiments, sending probes there to Enceladus, another satellite called Europa, in this case of Jupiter, to look for these things. But at the moment, I would say that this doesn't seem to me as very promising for life. What you really want to do is go to the exoplanets, which are much further away outside the solar system. This is a moon of Saturn in our solar system, okay, but the solar system seems a fairly barren place apart from the Earth, but why not go somewhere else where you have a better chance? So this is why we're so enthusiastic about going further to look for life. The Milky Way has billions and billions of stars like the Sun. So this is a recent map from the European Gaia satellite, which shows you hundreds of billions of stars, actually, tens of billions, I think, in this photo, and each of them have resolved as points of light, amazingly, by this telescope, and we know that many of these stars have got planets around them just from discoveries we've made already measured many thousands of planets around nearby stars, but just thousands. But if you have billions of stars, then there must be billions of planets and tens of billions of planets, because many of them have several planets. And of these billions and tens of billions of exoplanets, distant planets, some fraction are going to be not that dissimilar from the Earth. You would think, just statistically. That is to say, they must have rocky cores. They must not be too far from their host sun or too close. They must have atmospheres, perhaps oceans, etc., etc. We think, okay, but we don't know. And if they do, then they would be ideal sites for life, and then we have to look for those signs of life if there are any. So that's the enormous challenge. And it's incredibly hard to do with our current space capabilities. And so at this point, I think it's pretty clear that we cannot do this search from the Earth. And so we're basically, the largest telescope we have on the Earth is in Chile, in Atacama. It's under construction now. It's a huge telescope, 39 meters across, but it's not large enough to really resolve any of these stars, distant stars, well enough to look for those exoplanets properly to actually get an image of an exoplanet in projection against the host star, which you could do in principle. Okay, so that can be done, and ideally what you want to do is do more than that. It's not just the image. You want to look at the atmosphere of that planet far, far away, and look for traces of maybe human or whatever alien activity in the atmosphere, or else the ingredients like oxygen that would be necessary for life. And so far we're unable to do that really in any serious way. And the problem is you need not just meters, tens of meters. You need huge telescopes, kilometers across, to do this, to actually get the resolving power. It's as simple as that. Well, there are ingenious ways to do that. I'm going to show you one, and that can be done from the moon. And so this is something. The experiments I showed you so far from the moon are ones that technologically we know how to do. We've done it on the Earth, and it's, I think, not that great a step forward. What I'm going to show you now is a major step forward, but in principle, this is what's going to happen, not over, for the radio case, 10 or 20 years. In this case, it's going to take a bit longer, but not that much longer. And the idea is to have a kilometer-size optical telescope or infrared telescope. How do you do that? Well, the same principle as my inner crater radio telescope. You go to a dark crater on the moon, and you line up lots of small mirrors, okay, in basically a hemisphere, and then from the rims you string the focal point and the camera, okay, and suddenly you have a telescope that might be 10 kilometers across. That has the resolving power. Now, this is trickier than it seems, because each of these small telescopes has to have its beam connected to the other telescopes to make them one single telescope, one single beam. And that's a complication. We know how to do that so far on the Earth for 2 telescopes. To do it for hundreds is a whole other story. But in principle, we can do this. It should not be a problem. And once you can do that, you can suddenly get not the limited resolution we have from the Earth with our rather small telescopes, or from space for that matter, but from the moon we can do amazing things. And this is maybe the most amazing image of all. It's an artist's conception, let me say. So there's a nearby star with a system of planets around it. It's called the TRAPPIST system. And it has some 8 different planets. Now, these are artists' conception of what you could do, but it's just 40 light years away from us. So with my kilometer-sized telescope, I can really resolve those planets, and I can look for atmospheres, for signs of atmospheres, for signs of oceans. You'll see the glinting of the oceans from the sunlight. You see mountain ranges and the snow on the mountain ranges, whatever. All these many things you could suddenly do. And if there were city lights, you could see those city lights, etc. So there are many things you could do with this incredible resolution. And that will be the ultimate answer. And this was something we can only do on the moon. This doesn't need the far side. You can do this on the near side, but you don't want to do this in a crater near the moon. Okay, so let's see. So let me now turn finally to where we are politically, etc. So the big news now is that we're suddenly, after 50 years, we're able to reproduce the payload of the Saturn V launcher that carried the Apollo program on its back, as it were, to first men on the moon. And both NASA is doing that with its Space Launch System rocket that was launched last November in its first launch cycle around the moon, and in 2 years' time it'll go back to the moon with humans on board. Okay, so that's the plan, part of the Artemis program. Meanwhile, we have the private sector jumping in to do much the same thing, will do much the same thing with the SpaceX launcher of Elon Musk's company. The beauty of the SpaceX Starship is that it's recyclable. The problem with SLS is that it will cost some billions of dollars or pounds or whatever per launch, very, very expensive, but Musk is promising us so far that this will, well, it hasn't launched successfully yet, it had one failure, but it's going to basically be far, far cheaper to run. And similar projects, I should say, are under construction in China too. Okay, so let me conclude by telling you some of the problems that we're going to run into. So we're about to get all the carrying capacity we need to go to the moon and build experiments on the moon, do many things on the moon. That's coming in the next 2 years. Okay, so what is the problem going to be? Well, one problem is that the moon's going to be crowded. There are limited numbers of sites, you know, there's craters I've talked about near the poles. So maybe, maybe there are 10s, 50s. And what if more than one company, commercial company, because they're getting involved now, or country, we have both the US and China to start with, others are jumping in too. Just let me say parenthetically that there already has been a small launches to the moon from, for example, the last one was the United Arab Republics. That unfortunately failed, but that was just a couple of months ago, and before that there was an Israeli probe, etc. That was 6 months ago. Both of those crashed, but they're preparing new versions to go back to the moon with rather small projects, small lunar buggies or whatever. So it's becoming a huge international thing, but the big projects, of course, are being launched between mostly Russia and China. But the things that we're going to run into is the legality of all of this. So if one country gets to the moon first, and says, this is where I want to put my next factory or mine for ice or whatever, and another country wants to grab that too, who decides? Okay, so there has to be some sort of treaty to decide all of this. So there was, of course, an outer space treaty in 1967, signed up to by 100 different countries or more at the time. But the problem with this treaty, it says, no pollution, no military force on the moon, but there's no enforcement. So how do you enforce these things? So far, that has to be decided. And finally, I would say, with all of this going on, there has to be a role for science. So I think with all of this, with science, we'll address these amazing questions. Are we alone? What were our origins? I think that's what science can do. And then finally, I think there really are no limits to this. So thank you.
Time for some audience questions, if anyone has. Joe, yes.
I am interested to know, do you imagine that with all these telescopes, when they are eventually developed and in situ, how will you get the information to the Earth, or will all the progress happen on the moon itself?
Okay, so eventually it'll all happen on the moon itself, but in the meantime, the idea is to send relay satellites around the moon. And so they go from the far side to the near side. It takes a couple of hours, and they will relay stuff back to the Earth. So relay satellites. So we've done one of those already. It's fairly straightforward. So that will be the next step.
More pollution.
Sorry?
That means more pollution within the moon.
Pollution, you said?
Yes.
Yeah,
if
sure.
If you are sending information, you will create pollution for the satellites to be there without pollution.
Sure. So whenever you have satellites, they reflect light. They give you some light pollution. They may give you radio signals, radio pollution. All of that can be controlled if we plan in advance. So we haven't done that very well yet for the Earth. We're facing a huge crisis on the Earth now with pollution from small satellites as we make more and more of them. But from the moon, where we haven't really started yet, we have the chance to plan things better. So I'm hopeful that'll be controlled.
Oh, hi. The idea of building telescopes on the moon sounds really exciting. But does NASA have a definite project to do that? And if so, when is it likely to take place? And are the Chinese trying to do the same thing? Is there competition there?
Yeah, so I didn't have time to go into that, but yes, indeed. So first of all, NASA has launched a new program of commercial launches to the moon. In fact, those are the similar commercial launches carried this United Arab Emirates and Israeli probes. And so there are similar things now funded by NASA with American companies, and they are doing quick experiments, and three of the first involve radio astronomy to exactly set out the possibilities for doing this more advanced stuff I talked about. So in 2 years' time, they'll be launching a probe to the near side, actually, to see what the reflectivity of the regolith is like, because that's a big impact. And then after that, within a few months, they'll be sending a probe to the far side, a Pioneer telescope, to see, look back into the universe at low frequency waves. But more of a Pioneer, because it won't have really the sensitivity to the ultimate job. It doesn't have the battery power to last very long, but in principle, that'll do the job. And then at the same time, the Chinese are sending, again in 3 years' time, a flotilla of 9 satellites to orbit the moon. The beauty of that is it takes them, and they fly in formation, they act together like a giant radio telescope, and it takes them 2 hours to go around the moon, come back, and so they have enough time with their batteries to take the data, then transmit it back to Earth, etc. And so that probably is our best hope for the first glimpse of the Dark Ages. And so that all that's near term, 3 years, and then the long term, there are plans both in Europe and in China and NASA to build much larger telescopes, radio telescopes on the far side. That's the major thing that's being done, because we understand the radio technology much better than the optical technology. It's much easier. So we're going to start off in that direction. So all of that's under planning now.
Give us an idea of how, of the resolution of these telescopes compared to, say, the James Webb Space Telescope. I mean, is it going to be in orders of magnitude?
Yeah, so the radio telescopes have essentially no resolution. They're designed to look for just the global signal, see the Dark Ages actually against the backdrop of the universe. It's this crater-sized optical telescope that will have amazing resolution, and even possibly slightly smaller ones, and they will have, I would say, thousands of times better than the James Webb, possibly resolving things immensely better. So they will just take us back further and look for the exoplanets in far more detail than we ever could do any other telescope.
So this is really cool. The aspect of the science part of it, super sick, the telescopes and everything. However, if you talk to the average general person, it would just be the idea of, well, why are we going back to the moon? We've already been there. Elon Musk says that he wants to go to Mars, whether that's for science or because of his ego, we don't know. But how do we kind of prevent the over-commercialization of this? How do we make sure that when we do get to Mars, that these craters that are all perfectly formed for telescopes there, how do we stop them from turning into resorts? How do we get the public excited about the science rather than I want to go to Mars, no, I want to go to the moon to, I don't know, be in a hotel or something? How do we kind of get that?
Well, look, the moon's a stepping stone to Mars, that seems sure, but we've got to go there first to even have any hope of getting to Mars, to figure out all these various things and launching spacecraft. So sorting things out legally on the moon will be a real problem. Fortunately, we have some experience of that in the Antarctic, where the Antarctic treaties have worked, and we've avoided, legal grabbing and mass pollution. But of course, there's much less to gain from the Antarctic than there is from the moon. So there are huge commercial interests that will be in play, and I just think it's going to take some very delicate negotiations at the United Nations level to sort this out. And you need sort of maybe a better time than now to do this, but hopefully, we have 10 or 20 or 30 years to sort our act out together. I'm hopeful it'll be done, but there's no guarantee at all. I agree with you. It could be the Wild West all over again, for example, to give you the worst scenario.
Question up at the back.
Thanks very much. Following on from that question, perhaps more worrying than the commercial aspect is the military, and how do you, how do you resolve the conflict between the military having their own ideas and perhaps the benefit of mankind? Thanks.
Okay, I would say with great difficulty. It's particularly opaque in China, where their space agency, and the military aspects are a bit opaque. It's not that much better in the US, I would say, with NASA and other departments, doing both, of course. So I guess you just have to have international agreements. Right now, many countries have signed this agreement not to do military activity on the moon, but how you enforce that simply, there's no enforcement at this point. So we have to bring up some enforcement for that understanding. So hopefully that will happen.
One final question here.
I hope this might not be too big a question, but what is the biggest theory for what is happening in the Dark Ages right now? Or is that just too big for the end?
No, so the biggest theory simply is that nothing is happening. It's just a stage of assembly. But the reason we're so excited about that is because there are so many of these building blocks of clouds, is that once you start getting signals, you can use this all this information you suddenly get to study the origins of the universe, because it's all a question of information content, really. And right now, we're finding the universe is, beginning to accelerate recently, etc., etc. But our information simply is limited because we have just that many galaxies that we study in our surveys. So, maybe there's a billion galaxies in our latest surveys done with the James Webb, etc., and other telescopes. But if you can go back to the Dark Ages, because you have a million of these clouds forming every galaxy, you suddenly have trillions of these building blocks. The information gain is incredible. And it's by that you can then learn about where the universe came from. That's the idea, to study its mysteries.
Great, thank you very much, Joe, for such a fascinating talk and for answering the audience's questions today. I'm sure many of you are keen to get hold of a copy of Joe's book, which is being sold by our independent bookseller, Fox Lane Books, over here, and Joe is available to sign some copies for you. Please take a look in the festival programme as well for other events coming up over the next few days. But again, thank you very much for coming along, and thanks to Joe.